Um, Thanks everyone for attending today. My name is Kevin Farms. I work at the Argonne Leadership Computing Facility, and I'm going to tell you a little bit about things we're doing with DAOS at Argonne. And first, I want to start with just a brief overview of Aurora. If you've been here before, you may have heard me talk about it before, but I just want to give a little bit of background. Aurora is our new system that we're bringing up, and DAOS is going to be a component, but I just thought I'd give you an idea first about compute systems. So here we're using the Intel Data Center DPU Max, which everyone should know that that's PVC based on this excellent Intel marketing name. And then our processors are Xeon, Intel Xeon CPU Max, which is a Sapphire Rapids with HBM. So I will quiz you on that later. We also have our storage interconnect is HB Slingshot 11. All right, so I want to start with some background of like why is ALCF involved with DAOS and stuff. Obviously, on top of having it one of our storage systems, you know, what else have we been doing? And so we've been working with Intel starting around 2015 or so, working in a collaboration where we've been working with Intel on the design and the features related to our work. Of course, Intel does all the work. We're just giving them our feedback and things like that, but it's been a partnership. And so we call this process NRE, which stands for non-recurring engineering. And so I just put up 4 kind of current things that we're working on. There's been many things in the past, but some stuff that we're working with Intel on currently is this idea of supporting multiple loop fabric providers at the same time, so that would allow us to use DAOS on 2 different networks at the same time, which allow, we'll see later why that would be important, but we have cluster access to our storage system. Also, since it's a new storage system, and of course we have all these legacy codes we want to support, Intel's going to do some optimization on some codes that we gave them or we selected together, and then hopefully we can take that money and then bring that, create like training materials to help other users to be able to support their applications and get the whole out of that storage system. And then some more feature-related things, optimized object placement. So in the case of Aurora, it has a 1D dragonfly topology. And so if you place objects, actually, you might get slightly better performance. So if you're working with Intel to support some kind of topology-aware optimization. And then finally, supporting a catastrophic recovery failure in case something were to go tragically wrong with the storage system. It's kind of like the current things we're working on. So now I'll give you a little bit of overview. This is just abstract concept, but point out a few things. So one, I said before, we have a slingshot pattern. And so the gray box is hard to represent all the few racks. Again, it's just numbers here, the relative sizes aren't necessarily meaningful. And then the red boxes represent DAOS. And so you can see it's actually directly on the high-speed compute, which obviously gives you lower latency and higher bandwidth access to storage from these compute nodes, but that means they're not easily available in other systems. And so that's why we've been working on having some solution to be able to access the storage system outside of Aurora through using a different provider. So then we of course have our legacy file systems that we have for our site-wide thing, and those are connected on our own storage fabric. And then you see up here some key metrics about the storage system. So we hope to have about 220 petabytes of capacity if you assume that all of that capacity is dedicated to EC60+2. Users can obviously choose, so total capacity can float a little bit based on what users are selecting. And then our target of 25 terabytes. To give you some ideas like what the storage are built on. So these are Intel Coyote test systems with dual Xeons. They have Ice Lake CPUs. They have 512 gigabytes of RAM. And then the aggregate persistent memory, Barlow Pass, is about 8 terabytes. And then you can see then we have, you know, 15 terabyte Samsung SSDs. So that gives you about 244 terabytes. So we have roughly a 3% metadata to data ratio, and then 2 slingshot NICs. So we have in the system a total of 1,024 servers, but each server is sort of split into two. So we're running 2 storage engines. So one engine is on one socket, it has 1 NIC, and then it uses half of the resources above. So 8 of the SSDs, 8 of the DIMMs, so to speak. So we avoid kind of NUMA effects at the storage server level by running 2 on each server. And then the photo here at the bottom is just a picture. These are actually the Aurora storage racks, or also generally referred to as non-compute nodes. This is the back where all the networking is happening. So this is currently installed. All the equipment I'm talking about is actually currently installed at our not for testing. So I'll get to more of that later. To dive in a little bit more on the network architecture. So in this graph, this is like a cartoon of what the Dragonfly topology looks like. So kind of on this set of boxes here, over here, this is the compute groups. I won't talk about as much as that, but let's focus here on the IO groups. So we have 8 Dragonfly groups representing all of the storage servers. So all 1K nodes are within these 8 groups. And so you can see this purple line, we have an increased amount of links between the groups. This allows that, since our storage servers are actually on the compute fabric, we would much like it if the IO traffic between the IO servers doesn't leak into the compute fabric and interfere. And so one way to accomplish that is to give them more bandwidth or more links for traffic to flow over. So when the servers are talking to each other for rebuild, for general liveness, other types of communication, these can all go over these links without, hopefully, you can have indirect routes. So hopefully we don't have a server to server message going over one of these green links and then coming back. So this is why we've engineered these purple links. And then additionally, this service group here at the end, we have one of these. All of our gateway nodes, which if you remember that first graphic I showed you, there are some nodes connected to a storage fabric that's InfiniBand. Those nodes reside in this group. And so if you want to send data off the cluster, like for example, you want to transfer it to Luster, or some other similar data movement thing, you want to copy data, that's going to happen in the service group. And so then we again have some increased links between the IO groups and the service group to allow that to happen without again leaking into the compute fabric. That's kind of the idea of our storage fabric. I give you like an idea of what's happening with Aurora. So first of all, note all this work is being done by Intel. I'm just presenting it, but they did it all. Like I take no credit for the work done here. That's all their hard work. And so, like I said, we have all the hardware on site. We've done the initial hardware evaluation. So Intel's gone and more or less validated every server. Of course, some servers had some issues and those are still being resolved. But in general, all those 1,024 nodes have had some basic checkout done. All the hardware validated that it's there and generally working as unexpected. So then next, we moved on to testing. If we go back to this chart, doing servers with one Dragonfly group. So setting up a storage system that it resides fully inside this box here, okay, and then testing that, which that means that tests the networking that's represented just by these blue links. All right, so that's been tested. And so we've done that for each group independently. So at this point, we've kind of tested all the hardware and we've tested those blue links. And what's being done right now is, Intel has a set of basic automated testing that they can run, and they run that, and they've run that on all systems. And then they have some soak testing they can run, and that runs for an extended period of time, just running the same set of workloads over and over to make sure the system is stable. And so when we're testing, right now we don't have access to all the compute system. That's being worked on separately. And so for the DAOS testing, we either have to use the gateway nodes I mentioned, or we have to use other DAOS nodes as clients. And so that's generally how the testing proceeds. And so again, So the first order, we validated all of those 8 groups. So what's currently going on is what I'll refer to as scale-up testing. So now we're trying to do that testing, but now spanning, again, sorry for changing the slide, but spanning multiple groups. So now we might have servers in 2 of these boxes. They're in this same storage system. And now traffic's going to flow over these purple links as well as the blue links. So now we're validating all these purple links. And so that's, you know, the ongoing testing right now. And of course, we're hitting various DAOS issues as well as some network issues. Some of them are hardware related, as I said, validating the purple links. And some of those might be other switch problems. And we're using their hardware there that we haven't tested to this point. And so all of our work is being captured in the DAOS JIRA ticket. So hopefully everything that's happening on our system is valuable to everyone else's future systems. It's all there. You can go and take a look if you want to see what's going on. Next, I want to talk about another system that we call Sunspot. And so Sunspot you can think of as a baby Aurora. It's only 2 racks, so that each rack is a Dragonfly group. So it's got 2 groups composed of 2 racks, has a whole total of 128 compute nodes. With that system, it also has its own dedicated storage system, and that has 20 DAOS nodes in it. These nodes are identical to the server configuration for Aurora. So on the earlier slides where I gave you those exact same servers for this system as well as the main system. And so we chose 20 here because our target is to have our protection be EC 16 plus 2. And so with EC 16 plus 2, you need 18 nodes. And so if you have an 18 node system, but then want to be able to test the failure, and so have the server fail, then we need something to fail over. So then adding 2 more nodes, we can fail 2 nodes and still do rebuilds and then achieve full data protection of the 18 needed. So that's the concept for our 20 DAOS node system. So we can test all of this separately from Aurora. And so right now, the compute system we're working on right now, so we have the compute nodes and we're testing that. I was hoping that I could tell you that we have our DAOS running, but the admin who's working on the compute system still working through issues on that side, so he hasn't been able to provision our images for the storage side yet. But I hope in the weeks coming that this system will be up and running. And so I don't know if I can call it will be the first production environment, maybe. Anyone can argue if they're already production. But we'll plan to give users access to the system. And so at the top, you notice I put a link here. This has some of the information on it. So obviously, this is documentation for users. Obviously, the user can't use the system yet. We haven't provided access, but that's the basis of our documentation is there. And so the goal here is we're going to follow the model that we've developed for how we're going to use tools and containers on Aurora. So I highlighted in that previous talks, but I'll just mention it a little bit here. The main thing is at ALCF, when we hand out compute time, we do so as a project basis. So someone submits a project, there's different allocation policies, but the particulars don't matter. But you submitted a project request and how many hours you want on the compute system. At the same time, you can say how much storage you want. If you don't say it, then we'll give you a default. And so for each project, we'll allocate a pool. So that means that they get physical storage assigned to their project. And so how are we going to deal with that pool? So our current plan is to take, 60 to 80% of the targets available in this 20 node system, and put their pool on that. So that means they can achieve, most of the bandwidth that's possible. And then we'll set the ACLs for their pool based on what they've requested. So whatever project members they've asked for, they'll all be in the pool and they'll be able to create containers. Then at that point, the users can choose to create their own containers, which is good and bad. That means they have total flexibility on how to choose it. Of course, they can choose to do things maybe not wisely. So hopefully we're planning to have some scripts to help them create a container following what we would consider best practices. So they can use that and then help them. So for example, making sure if they don't have a choice to use EC 16 plus 2 as a starting place. Obviously, if you're a more advanced user and you know, hey, I have this workload and this is only temporary files, I discard them at the end of the run, maybe you'll choose to have no replication for that data while you're running, because if it crashes, you're going to go back to a checkpoint rather than anything in files. Then hopefully, as I spoke before, we have this 3% ratio between our metadata and data. And so we can examine if that was a correct call or not. So we chose that originally based on, we have like 5+ years of storage data from an old system. We analyzed that and said, okay, how much do we need? It was less than 2%. And so we believe we're okay with the storage ratio, but we'll start getting to vet that out on the system. Next couple of slides, there's some advertisements I have. We did make an IO 500 and submitted results. So the IO 500 block is tomorrow. So if you come by, you can see our results. Hopefully they're good. You'll get to see more of those. Please check it out. And then finally, this is my most important slide. So please look at this slide. Back to work on DAOS. So if you know someone, there's the link, there's the information. You haven't contacted anyone at ALCF. I would much like to hopefully come away from SC with someone who's interested in being close. Yes. Yeah. Okay. So the question is, how does it handle applications in the case of failure? Okay. Right. Okay. Okay. How do we foresee bringing applications into the system, and what will be the best route? So we've had some discussion on that. Obviously, so we have another test system that I've mentioned in the past, but for various reasons, it had only a few CPU-only clients, and of course, this is a GPU system, so all the people working on it, developing GPU code, it wasn't runnable on most systems because they need GPUs. Most people have the way they develop their code, it just requires GPUs. So we haven't had a lot of testing done. We work with Intel on certain applications, but to start with, we'll just say to use SKUs. So one advantage is, even though we're using one NIC on one compute node, the idea is people are running large-scale jobs. So even the individual I/O coming off each compute node is slow, you should be able to start to get to a point where you're saturating the storage system, even with that model, if you run at large enough scale. Secondly, we do have a lot of users who have transitioned to NPIO because that's been a push from Argonne since our first system. And so I think the NPIO backend is quite good for DAOS. So if you use NPIO, you should get good performance, and it works on the POSIX layer. So then if you have other tools for analysis, you don't need to worry about like, how do I make that use a special container? You can just use your POSIX tools. Interception library, I'm hoping we don't need too often. That would be for people who just have pure POSIX only code and no other IO backend. We'll see. There's definitely some people that come up with those. The main thing I'm worried about is, from my experience of working at Argonne for quite some time, is a lot of people come to the system with no idea how the IO backend of their code works. And so if you ask them how it works, they don't know. To give an example, we collected a long time ago the top 10 users of our storage system, and I went to each one asking them, and I got a response back from like the number 5 user saying that they don't do IO. So it's definitely a hard road, and so I'm not sure how it will go. But unlike certain labs where there's some people that we know very well that are like local to Argonne, or even if they're at another institution they've run in Argonne a long time. Of course, then we have other users that come in. You don't know anything about them, so it'll definitely be a learning experience. So I can't give you a positive answer. It's going to be good or bad, but I know it'll be a challenge for sure. Yeah.